Okay, so next we'll look at some of the properties of a transpose. First, the transpose of a transpose is the original matrix. Second, the transpose of a sum or difference is the sum or difference of the transposes. Third, the transpose of a scalar multiple of a matrix is the scalar multiple of the transpose of that matrix. 4. The transpose of a product is the product of the transposes in reverse order. All right, so we will prove these statements. First, the component in row I, column J, or rather the entry in row I, column J, of the transpose is the entry in row J, column I, of the transpose of the matrix A, which is the same as the entry in row I, column J, of the matrix A. And so the transpose of a transpose is the original matrix. All right? Second. Oops. The component in row I, or entry in row I, column J, of the transpose of a sum or difference is the component in row J, column I, of the sum or difference. And this is the sum or difference of the corresponding entries. And the entry in row J, column I, of the matrix A is the entry in row I, column J, of the transpose of A. And the entry in row J, column I, of the matrix B is the entry in row I, column J, of the transpose of B. And so we have that the transpose of a sum or difference is the sum or difference of the transposes. Right? Third statement. The component in row I, column J, rather the entry in row I, column J, of the transpose of the scalar multiple of the matrix A is the component in row J, column I, of the scalar multiple. And this is the same as the scalar multiple of each component. And so we have the scalar multiple of the component in row J, column I, of the matrix A, which is the same as the component in row I, column J, of the transpose of A. And so the transpose of a scalar multiple is the scalar multiple of the transpose. Fourth. The component in row I, column J, of the transpose of a product is the component, or rather the entry, in row J, column I, of the product. And this is the sum over the index K of products of entries in row J of matrix A and column I of the matrix B. And so this is the sum over the index K of the component in row J, column K of the matrix A is the same as the component in row K, column J of the transpose of A. And the component in row K, column I of the matrix B is the same as the entry in the entry in row I, column K of the transpose of B. Now these are simply entries. They are numbers, and so we can switch the order. And so we have the sum over the index K of the products of the entry in row I, column K of the transpose of B, and the entry in row K, column J of the transpose of A. And this is the element in row I, column J of the product of the transposes in reverse order. And so the transpose of a product is the product of the transposes in reverse order. All right? All right, so let the matrix A and the matrix B both be M by N matrices. Then the product of A and B is not defined since they are not conformal. The product is not conformal. But a transpose B, if we pre-multiply the matrix B by the transpose of A, then this product is the N by N matrix with entries given as the sum of the product of entries. So the entry in row I, column J of the product A transpose B is the product of entries in row I of the transpose of A and column J of the matrix B. All right. So now would be a good time to introduce what is known as Einstein's summation convention. And this is a notational convention that simplifies expressions involving sums. And the convention is that if a given index appears twice in a term, then this implies a sum of the product of these terms over all possible values of the index I. And so this is the sum over the index I of c sub I x to the power of I. So by using this convention, we can simplify these expressions and merely show the product. But when we see a product whose terms include an index that is repeated twice, then this means, this implies a sum over those products over all possible values of the index I. And so we can simplify the expression for the entry in row I, column J of the matrix of the product matrix AB to be the product of the entries in row I and column J of the matrix, row I of the matrix A and column J of the matrix B. And again, as the index K appears twice, this is implied to be the sum over all possible values of the index K of these terms, A sub ik, B sub kj. Right? So now a new definition. A permutation of the subset of positive integers from 1 to some positive integer n, is an ordered arrangement or an arrangement of these integers in some order without any omissions or repetitions. And we generally denote the permutation with subscripts separated by commas. For instance, j sub 1, j sub 2, and so on up to j sub n. And this is an ordered arrangement of the positive integers 1 through n without omissions or repetitions. All right? So now a new definition. An inversion occurs in a permutation J1, J2, and so on to Jn if a larger integer precedes a smaller one. So using this, we can define the parity of a permutation, that is the even or oddness. A permutation is even if the total number of inversions is an even integer, and the permutation is odd if the total number of inversions is an odd integer. So we need to look at an example and learn how to count the number of inversions. So for example, 3, 1, 2 is a permutation. Of the positive integers 1, 2, and 3. Now, when we count the number of inversions, we start on the left and go towards the right. So the number 3 precedes both the number 1 and the number 2. And so this is 2 inversions. And continuing to read left to right, we next come to the integer 1, which is not larger than the number 2, and so this is the total number of inversions, and that is 2. And so the permutation 3, 1, 2 is even. Quickly, we'll look at another. Look at the permutation 3, 2, 1. Again, reading from left to right, the number 3 precedes both the number 2 and the number 1. So this is 2 inversions. And then continuing to read from left to right, we next come to the number 2, which precedes the number 1. And so this is 1 inversion. So we have a total of 3 inversions. And so the permutation 3, 2, 1 is odd. Right? Now recall that the number of permutations of n objects taken r at a time is defined to be n factorial over n minus r factorial. So the permutations of the integers that we were speaking of are permutations of n integers taken n at a time. And so we have the number of permutations of n objects taken n at a time is n factorial over n minus n factorial, which is n factorial over 0 factorial. 0 factorial is defined to be the number 1. And so this is simply n factorial. And of these, half are even, and the other half are odd. So for example, given the set of positive integers 1, 2, and 3, there are 3 factorial, or 6 total permutations. Three, or that is half, are even, and 3 are odd. Right? So next we define a new type of product that comes from a square matrix. An elementary product from a square matrix of order n is a product of n entries from the square matrix A, AJ1, 1, AJ2, 2, and so on up to the nth term, AJNN, none of which, or for which none, no 2 entries are from the same row or the same column. So in other words, an elementary product from a n-order square matrix has as its subscripts of the entries the A permutation of the first n positive integers, and we're ensuring that we're taking a product of n of those. So an elementary product is a product of n entries from the square matrix for which no 2 entries are from the same row or the same column. In other words, there are no repetitions and no omissions, since there are n total entries. So a signed elementary product from a square matrix A is an elementary product from A multiplied by either +1 or -1. We choose to multiply by +1 if the permutation J1, J2 up to Jn is even and we choose -1 if the permutation is odd.